So in this case, we can start the next lesson. Is somebody tall enough to push this button there?
Which one?
Hold on, maybe not. Wait.
No. Yeah.
Oh, well, and knock off entire projector. Okay, we are getting it. Good. All right. So in order really to model nature, we will develop certain concepts, relate them in appropriate way, and which describes nature, and from this we will form a theory. Well, concepts are like the first words in a theory, and in order to for the theory to be useful, we have to understand the concepts, and you will have a lot of problem with comprehending what is what of what. You will have some kind of intuitive understanding, but in engineering you have to be precise about it. Even if something is imprecise, with a high precision you have to know how imprecise that thing is. All right. Now, concept is an idea used to analyze certain aspect of nature. Now, we can have either a primitive concept, and a primitive concept is such that we have only intuitive understanding. It's something like the first words. It does not have a definition. And we have concepts which are expressed in terms of other concepts. If we express one concept in terms of other concepts, then it is a defined concept. The relationships between the concepts could be either axioms, sometimes we can call it postulates. So it is a relationship between concepts which we assume that it is true. The only justification for validity of this relationship is that it agrees with the experiments which we have performed so far. Now, experiments which we performed so far include also our creations. So if we build a certain type of aeroplane, and if it works, it means that that so far the background or the theory which we used to build this aeroplane was correct. But if we built a spacecraft or an aeroplane using our common model, and that plane does not fly, so we consider that this is a negative outcome of an experiment. That failed plane becomes automatically an experiment. And then we will verify if everything was satisfied in the theory, and if everything was satisfied in the theory to build this aeroplane, and that aeroplane does not fly, what is the conclusion? The theory is bad. We have to revise it. Correct. So we have to change the axioms. The axioms. We cannot use the axioms which led to a wrong conclusion. If a relationship between concepts is obvious by looking at some other relationships, in other words, it can be proven, then this relationship is referred to as a theorem. Well, if we put all three together, so a set of concepts, axioms, and the theorems combined together form a model which represents nature, and this model is referred also as a theory. All right, so now it's the time to introduce some concepts. We will start with the simpler concepts, which are referred to as scalar quantities. And scalar quantities, well, in general, character of a physical quantity is determined on this: what are the rules of their combinations. I know that if you read the book, probably you extracted two pieces of information, what makes a distinction between scalars and vectors. And those pieces of information are that scalars have only magnitude, and vectors have magnitude and direction. Now, this is only half. This statement is true, but I don't want you really to take this statement as a criterion for defining vectors and scalars, because sometimes we have quantities for which it's not obvious what is the direction of that quantity. For example, if I spin, we'll introduce a vector quantity which tells us how I spin, and this vector quantity is called angular velocity, and it really says, well, how I spin. Yeah, so tell me what is the direction in which I spin. Counterclockwise, for example, right? I mean, how did you figure out that I do it counterclockwise? I think counterclockwise would be that way for you, right? Well, I'm spinning this way, so it isn't counterclockwise. Besides, now, show me the direction at which you see me. Show me it. All of you. Well, no, definitely not that way. You don't see me this way. Where am I? Yeah, my question is, where am I? Show me the direction toward my location. All of you. Right. You stretched your hand. Well, do the same thing with my spinning. Stretch your hand in the direction in which I spin. Yeah, so I spin this way. Oh, why did you figure out that I'm spinning that way? I have no, I mean, see, it is not that trivial to assign the direction to the way I spin. Well, it's the other way around, actually. If we recognize that a certain quantity is a vector quantity, then we can identify magnitude of that quantity, and we can identify direction of that quantity. Now, we are going to do it with the direction. We are going just to, because it is arbitrary. Now, if I walk, for example, if I walk this way, what is the direction of my velocity? Show me. What is the direction of my velocity? Now, who told you that this is the direction of my velocity?
Intuition.
What intuition? Well, no, I mean, our intuition is based on our experiences. It is that you even don't remember when you were taught that your velocity is in this direction. You heard it from somebody. Now, indeed, we will agree that my velocity is this way. However, if I walk only on the floor, it would not change our prediction if I say that my velocity is this way. I can also make calculations and predict where the object would be if I say that velocity is to my left. Now, why do we do it forward, not to the left? Now you can say it. Because it's more intuitive. Yeah, it's easier. So we assign those things in the easiest way it is possible. If we have a certain quantity and we recognize that that quantity is a vector quantity, we have no problem to assign direction. So, for example, for that spinning, we will learn in the future actually yet again. We use the simplest way to do it so that it is unambiguous. And clockwise and anti-clockwise is obviously ambiguous, because if I, for example, get over here and I will start spinning my hand like that, how do I spin it? Clockwise or counterclockwise? Counterclockwise. Do you agree? Clockwise, right? They say that clockwise, these people say that counterclockwise. However, so I mean, this is not a good way to describe the direction of rotation. It's better to use right-hand rule. It's also very as artificial as saying that velocity is forward or to the left. We align these fingers in the direction like surface of my body moves. Yeah, so if I turn that way, well, my surface moves around like that. Yeah, so I can curl my fingers this way. Thumb shows the direction of my angular velocity. So if I spin this way, angular velocity is up. You will have to learn that. It will be obvious for you in half a year. I know that right now it's confusing. Try to figure out which way Earth spins. I mean, in this classroom, show me the direction of the spin of our Earth. Okay, some people say this way. Some people say this way. I mean, this way is not good. I mean, it's as good as saying that this is the direction of my velocity. I want you to show the direction by stretching the hand. That way is already better. However, what would the people on the other side of the Earth say? Then it's wrong. We have decided, because now figure out in what direction I spin. I have already told you that. Up, right? It's up. Use the same rule for the Earth. Very good. This way. Yeah, it's really it's a direction between south geographical pole and north geographical pole. So it will be toward the North Star, and North Star is somewhere there. No, maybe there. Okay. So how we combine quantity determines if the quantity is scalar quantity, vector quantity, tensor quantity, and so on. All right. Scalar quantities are quantities which follow the same rules as numbers. And each scalar quantity can be represented by a single number. Amounts are, for example, scalar quantities. If I have one set which contains this many elements, and another set which contains this many elements, if I combine those two sets, this is going to be the number of elements. Well, you could figure out that actually it was 3 plus 2 equals 5. There's an amount of this set plus amount of this set is equal to amount of this set. Amount and number are two different things. Don't confuse those. Right? Number is a mathematical concept. Amount is a physical concept. I know that right now you even don't distinguish those. I mean, right? You have a problem to say that it's different. All right. This is the first description of the first scalar quantity which we are going to discuss. It's time. Time is a quantity which is associated with the changes in the universe. If we didn't have changes in the universe, concept of time would not make sense. What would we need it for? It will be like a fifth dimension in space right now. Yeah, because show me, where is that fifth dimension? You don't even think about fifth dimensions because we live in 3 dimensions. So if we didn't have changes, concept of time would not make sense. We assign, I mean, word time actually has a double meaning, so sometimes we can get confused. So let's start with the first one, that it is a number which is assigned to a configuration of the universe. For every universe, for every configuration of the universe, we assign a certain number, and we call that that number time at which a particular configuration happened. Which actually immediately says that movie Back to the Future does not make sense from the physical point of view. Why? Who watched? Who saw it? Who remember the main character? The guy, the boy who is moving back and forth. Marty, correct. Yeah. It is impossible for Marty to go to year 1955. Why?
Because his state did not exist in 1955.
Correct. Because he violates, even if the rest of the universe is like it was in 1955, his presence ruins it. So he cannot go to year 1955 because in that configuration to which we assign number 1955, he did not exist. If he appears over there, it's a different time. All right. Now, with that configuration, actually, it is that everybody would have to, or everything, every piece of matter would have to be exactly at the same position, and we will have to move exactly the same way. Then we will have a repetition of time. I mean, then we will loop the time. Well, when we will get to laws of thermodynamics, we will see that it's impossible, because we have some quantities, like one of the quantities which has this property is called entropy. And entropy does not, it always grows. So we cannot come back to the same value of the quantity. So, and actually entropy says about the configuration, says something about the configuration of the universe. Probably some of you heard about it, that entropy refers to this, how disorder is the system. What is the disorder of the system? It's a measure of disorder of the system. And when entropy grows, it means that the system becomes more and more messy. And this happens with the universe. Universe becomes more and more messy. And that mess already changes the configuration. All right. Now, the time is a primitive concept. We do not have a definition of time. We only have a certain procedures how to assign the value, but we cannot calculate it. So we assign a value by finding a clock. And actually here is a model of contemporary clock. I don't even want to go into details. It is atomic clock. However, important thing is that in every clock we have to find a certain process which repeats itself. Now when it repeats itself, please silence that cellular phone. When it repeats itself, it has to, well, we pick something which to our feeling, is very periodic. So historically, for example, we pick one of the objects which we thought that well, is very periodic. It was what? Sun. More specifically, it was Earth, right? The rate at which Earth is rotating. Now, the problem is that we are slowing down. Earth turns slower and slower and slower, and we will be continuing to slow down until the moon is fixed on the sky. So we would see moon from one place of the Earth, and we won't see it on the other side of the Earth. It would be from the moon we would see the Earth exactly the same way as we see moon from the Earth. Have you noticed that we only see one side of the moon? Always. Yeah, it is because Earth has already succeeded to suppress the rotation or slow down the rotation of the moon. It's slowed down to such a rate now that it orbits at the same rate as it spins. Anyway, so rotation of Earth is not that good, periodic phenomenon to use as a clock, because in every clock, when we find something which is periodic, we just count how many periods happened from a particular instant, and we will assign, which we choose arbitrarily. We choose a certain instant arbitrarily. We say that this is our 0 for time, and then we count how many times clock repeated its periodic phenomenon. Now, if the phenomenon, if event happens after the instance to which we assign value 0, that time is going to have a positive value. If something happens before, then we would assign negative value to time. All right. So one meaning of word time is that it is a quantity which is assigned to a particular instant. Each instant has its time. Well, SI unit is 1 second, and actually, well, this spectral line of cesium, cesium atoms are flying over here, has to perform a huge number of oscillations actually for 1 second. It doesn't matter how. It's better actually to use stopwatch than this clock. This clock is just because it's very stable. We use this clock because it is very stable. All right. So we assign now commonly, for example, if we don't use seconds, give me another unit for time. Minutes, for example, right? This is not a standard international unit because it's not a multiple by a power of 10 of a second. However, it is commonly used all around the world. So minutes, for example. Another one. Hours, correct. Hours. No. If I ask you what time is it now, let's say that it's an integer number. What time is it now? 8 what?
8 hours and 26 minutes.
I see that you switched to Star Trek vocabulary. Let's meet in 2400 hours, right? This is how they would say. No, you wouldn't say that it was 8 hours, 25 minutes. What is the time now? Forget the 25 minutes. Just 8 what? It's what?
26 a.m.
No. 8 o'clock. Yeah, it was 8 o'clock. Right. This is the time which we assign to an instant. Now, we assign 8 hours to something. We would assign 8 hours to what? Which is the other meaning, it is used for the other meaning of word time. Duration, correct. So, for example, I had to drive from here to Louisville, for example, for 8 hours. Yeah, we don't say 8 o'clock. We don't travel 8 o'clock, we travel 8 hours. However, the time now is 8 o'clock. Unfortunately, for minutes and for seconds, we use the same unit for both meanings, for the duration and for the time assigned to an instant. All right, so make sure that you don't confuse these two concepts. And don't confuse it with many more concepts, because 2 times 3, for example, that times has nothing to do with that physical quantity, not mentioning the journal. All right. Now, the second primitive concept which I wanted to introduce today is distance. We don't have definition of distance either. We just have a description how to do it. And distance is a scalar quantity which is associated with arrangement of 2 points. If I have 2 points, I assign a certain number to their relative position. It is assigned in such a way that it has to be greater or equal to 0. Distance from one point to the other point is the same as distance from the other point to the first one. It also has to satisfy various properties. So, for example, if we consider 3 of us, what's your name?
JT.
JT?
Mm-hmm.
Okay, and you?
Holland.
Holland. All right. If I compare distances between JT and me, and Holland and me, if I take square of this distance plus square of this distance, it cannot be less than square between their distance. Distances have to, well, actually no, even distances, we don't have to take squares. The distances have to satisfy such a condition that the number which we assign for this distance between these 2 points and these 2 points cannot be less, the sum of those two cannot be less than this distance. Can be equal though. The SI unit of distance is 1 meter. I was really kind of interesting if you read the history of 1 meter. It is that we are stuck actually with this what forefathers did. First they picked it as a part of a circumference of the Earth, and it turned out that they measured it wrong. So then the meter was not really that fraction of the circumference, not mentioning that at that time I think they thought that it's a sphere, and it isn't. So they ended up, they meticulously performed calculations and made a piece of metal, which actually, about this long, and they kept it in Sèvres near Paris, where the International Bureau of Standards for the entire world is. So later on they decided, what the heck, let's say that this piece of metal over there is 1 meter. And then the problem occurred that when we need higher and higher accuracy, then fact that piece was that the length of that piece was dependent of this if it was hot or cold, then there was another problem. So eventually we ended up with expressing 1 meter in terms of distance traveled by light. This is how the light will travel 1 meter at this time, 1 over such a complicated number of a second. And now this is the standard for for 1 meter. Now, why did we pick up speed of light? Because, as I said yesterday, it's fixed. No matter who looks at that, it's always the same. All right, the last item, the last physical quantity, which primitive physical quantity, which I want to discuss, is mass. And mass is describe an inertial property of objects. Now, inertial property is, we'll learn about this pretty soon. Inertial property is how easy it is to change the motion of an object. So how easy it is to stop it if it is moving, and if it is not moving, how easy it is to make moving. And as I understand, right now, this is the only quantity which is for which standard still is an object. The 1 kilogram is defined as the mass which a particular cylinder has. And this particular cylinder is also kept in that International Bureau of Weights and Measures in Sèvres. This is picture from Sèvres. The cylinder is 30 millimeters high, and its diameter is 39 millimeters by 39 millimeters. Diameter is also 39 millimeters, which actually reduces, for a cylinder, it is the largest volume of the cylinder at the smallest surface. So, because with that object there is also a problem that it can oxidize, for example, and then it is going to change mass. We don't want to have a standard which is varying. All right. Now, this 1 kilogram is such an object, actually, that that's it. Okay. Here is a picture of that standard. However, this picture is taken from an American version of it. All right. Now, when we have those primitive concepts, we can define some concepts. And the first one which I want to define is the length. Length is a scalar quantity which is associated with the size of an object. So if I have a line, for example, I can assign length to it. And whenever we have defined quantity, it means that we can write a formula how to calculate it, not just a story how to measure it, but we have a formula how to calculate it. And understanding of concept of distance is necessary to introduce concept of length. If I want to assign length to this object, I have to choose a sequence of points along this object, and then I can determine what is the distance. Well, we have already introduced concept of distance, so I can assign distances to that sequence of points. If I have those distances, I have to add them. I'm adding all those distance of between the sequence of points along the line. I will get a number. Well, then I have to include more points in between, for example, and again add distances. I will get another number, and I will have to continue doing it. So I will forever, actually, in principle. So I will get a what? A sequence of numbers. Now, these numbers will be approaching another number. They will get closer and closer and closer to a particular number. And that number is assigned as the length of the of that object. So now, when I introduce more and more of those points, I have to make sure that the distances between the consecutive points get smaller and smaller. So I cannot, for example, add a lot of points over here and none there, because these distances don't approach 0. I have to choose them in such a way that distances between consecutive points, any two consecutive points, get smaller and smaller and smaller. This is how we write over here. Yes, so we would read that the limit of this sum is equal to the length. Now this is an awkward notation, so rather than writing it that way, we use this S for the sum. And so it is a sum along the curve of, and now ds, if I compare ds to delta S is relatively, is large compared to ds. So this ds takes care that the distance becomes smaller and smaller and smaller. Well, those of you who already had calculus, you can recognize that we call that expression on in a certain way. What do we call it? An integral, correct. Now, this is again a question to those of you who had already calculus. What integral? Let me give you a hint. So it will be definite or indefinite? Definite. This is definite integral. Now, if I calculate a definite integral, well, it will be like calculating this sum over here. Now, limit of the sum, so I have a certain curve, I calculate limit of this sum, and as the result, I will get what? Well, let's see. What am I going to, these distances? They are numbers, right? If I add them, I will get a number. Okay, now the sequence of numbers will converge to a number, correct? Of course. So over here I have a number, which means that this is a number. Length is a number. We assign number to a length. Now, if you go a few slides back, you can recall a statement that every scalar quantity can be represented by a number. Length is a scalar quantity, and therefore we assign a number to it. Yeah, and now I want you, and when you are going, well, on the way home, I want you to think number, because it's a very important mathematical concept which we use for scalar quantities. Next week you will have to say vector, and actually look around yourself and think what is represented by a number, not now, but when you walk home, what is represented by a number and what is not represented by a number. All right, now, those of you who had calculus, what is the difference between definite and indefinite integral? Yeah, over here we already found out that if we calculate definite integral, the result is going to be a number, correct? Well, at least for a number-valued function. Now, those of you who had calculus, when you take indefinite integral of a function, what are you going to get? A function, right? Yeah, if we integrate x, we are going to get function y equals x. When we integrate that, we will get function y equals 1/2 x squared, correct. this is the question only to those of you who already had it. Now, those of you who didn't have it, you will learn it here, so calculus will be piece of cake. All right, let's now take a look at some examples. So, how about if we find circumference of a circle? You probably know already the answer. If I take a circle of radius r, its circumference is 2 pi times r, correct. How do you know that? How do you know that? Well, somebody performed this calculation and just gave you the final formula. Now we will recover that. So if civilization actually collapses, and there are no books in which you can find it, you will be able to recreate it. We will not have to go through entire history of humanity. All right. So first of all, I will calculate just length of half of the circle, this upper part. Well, along this upper part, I can write the relationship between x and y. So these points along the circle satisfy this equation that square of y component is equal to square root of square of the radius minus square of x component. In other words, actually, I wrote that if I choose a point over here, the distance from the origin to the point is equal to r, yeah, because from this one I can write down that x squared plus y squared equals r squared. All right. Now, I will consider now just one of the fragments, and I choose those points already close to each other. Although I didn't draw them, you have to imagine that these 2 points, this point and this point, are very close to each other, and their difference in the vertical component is dy, and horizontal component is dx. Well, this distance over here from this point to this point, I mark it as dl. Now this dl is, because now I have to add all those dl's. From Pythagorean theorem, I can recognize that distance from this point to this point is equal to square root of square of this distance plus square of this distance. So this square root is just dl. Now L of entire circumference will be twice the length of half of it. So this is why I put this 2. And here I'm going to integrate only over the top part. So I'm going to add distances only along the top part. Well, from this relationship, actually I can, if I want to factor out dx from this, I will, and outside of square root. So I will be left with 1 over here and a ratio of dx, dy over dx, and it will be squared. And, well, when we integrate, this is something which actually only those of you who had already calculus will probably follow. We have to specify, we have to select an index which we use for that addition. In other words, we call it variable of integration. And since I pulled out this dx, it makes sense to choose x as the index identifying the consecutive points. So x is variable of integration. Then I have to say what is the range for for this variable and mark it above and below that symbol for the sum. So I can recognize that the lowest value for x is over here, and it is minus radius of that circle, and the highest value for x is on this side, and it is positive value for r. Now, those of you who had calculus also recognize that this quotient happens to be, it's not that difficult to determine from this expression, because we invented appropriate operation. What is that operation? To find that quotient. What is it? Derivative, correct. Those of you who learned already how to calculate derivatives, you don't have to fight evaluation, to determine that quotient, you can recognize that it's equal to the derivative. So here we have to take derivative of this function. Well, derivative of this function, well, it's a composite function. So it is a function of a function. Over here, when we take the argument, first we have to square the argument. So we have a quadratic function. Then we have to multiply it by -1, add a certain number, and then take square root of that. So it's a composite function. When we calculate composite function, we use a procedure which is referred to as the, those of you who had calculus, how do we calculate derivative of a composite function? Chain rule. We use the chain rule. So using chain rule, we would evaluate that this is the value of the derivative of this function. I want you actually to, by tomorrow, or at least this week, I want you actually to study, no, more than that, to memorize appendix, this mathematical appendix. You don't have to memorize the tables, but the rules for calculating derivative. And actually see, you will be able, we won't have to remember the derivatives in this class. You can always use those tables. But acquaint yourself with the tables. Yes, it is at the end of the book. There is a supplement. Well, this is just an algebraic simplification of that expression over here. And also, if you take a look at the back of the chapter, you will find out formulas how to calculate indefinite integral of this function. And indefinite integral of this function over here, it happens to be r times arc sine of x over r. Now, indefinite integrals are useful to calculate definite integrals. In physics, we more frequently deal with definite integrals than indefinite integrals. And from my point of view, the purpose of indefinite integral is just to calculate definite integral using a very important theorem in calculus. And those of you who had calculus, can you recall the name of that theorem which allows you to find a definite integral from indefinite integral? The first fundamental theorem of calculus. Correct. So if I use the first fundamental theorem of calculus, I will find, what I have to do is I have to substitute for x the top limit and the bottom limit. If I do it, I will have pi over 2 over here and minus pi over 2. When I add this, I will get expression 2 pi r, which should make us happy. Why? Are you happy?
Sure.
Why?
Because that's the formula that we were taught.
This is the formula we know, right? We got it. Yeah, so we got it. This is how it is derived. So this will be all for today. See you tomorrow.